look at the idea of limits of a multivariable function. Let's suppose we have some function f of xy, and we want to find the limit as the point xy approaches a given point ab of f of xy. The idea is we let x and y get closer and closer to the point ab, and we want to be able to make f of xy as close as we can get to some point L. This will be the idea of a limit. Let's consider the limit as xy approaches 1, 2 of 3x squared minus 4y plus 2xy. I can plug in my number for x and number for y and see what happens. That would give me 3 times 1 squared minus 4 times 2 plus 2 times 1 times 2. This would be 3 minus 8 plus 4, or negative 1. So in this case, this limit is equal to negative 1. Let's look at the limit as xy approaches 0, 0 of x over the square root of x squared plus y squared. This time, if I just stick in a number, 0, 0 for x and y, we can see that we'll get 0 divided by 0, which will cause a problem. So instead, let's think about this in different ways. Let's start by supposing x is actually equal to 0. In that case, this becomes the limit as y approaches 0 of 0 over the square root of y squared, which is the limit as y approaches 0 of 0. So that limit would be equal to 0. On the other hand, let's let y be equal to 0. In this case, we have the limit as x approaches 0 of x over the square root of x squared, which is x over the limit of x approaching 0 of x over the square root of x. And this limit actually does not exist. As we approach 0 from the left, we are getting closer and closer to negative 1. If we approach 0 on the right, we're getting closer and closer to 1. So we can conclude that this limit does not exist, since I found a way for it to not exist. If I let y be equal to 0 and look at what's happening along the x-axis, I can see the limit is not going to exist. In general, if my function has two different limits as xy approaches ab along two different paths, then the limit does not exist. So let's look at another example. Let's consider the limit as xy approaches 0, 0 of 3xy over x to the fourth plus y squared. Let's start by letting x be equal to 0. In this case, we'll have the limit as y approaches 0 of 0 over y squared, which is just 0. On the other hand, if I let y be equal to 0, that would give me the limit as x approaches 0 of 0 over x to the fourth, which would also be 0. So far it looks like the limit of this function is going to be 0. But let's consider some other paths. Let's let y be equal to mx. In other words, we are approaching the origin through a line. M is the slope of my given line, and I'm going to pass through the point 0, 0. In this case, I'll have the limit as x approaches 0 of 3x mx over x to the fourth plus mx squared. Simplifying this, we have the limit as x approaches 0 of 3mx squared over x to the fourth plus m squared x squared. I can factor out an x squared, and when I do, I end up with 3m over x to the fourth plus m squared, or x squared plus m squared. I can now plug in 0. I get 3m over m squared or 3 over m. And this is not necessarily equal to 0. If the slope of this line was 1, then my limit is equal to 3. If the slope of this line was 2, my limit is 3 over 2. I can now see that this limit does not exist. Approaching along different paths gave different limits. These two gave zeros, whereas this one gave 3 over m. So this limit would in fact not exist. To show a limit doesn't exist, we need to find different paths that give different values. Like my last example, I had paths that gave 0 and paths that gave 3 over m. However, we can never conclude that a limit of a function exists by just considering its behavior along different paths. Generally speaking, proving a limit exists requires a much more careful argument. Let's consider the limit as xy approaches 0, 0 of x squared y squared over x squared plus y squared. So first off, let's notice that if x or y is equal to 0, then in that case, this limit is just going to be equal to 0. And you can verify that, but either way, if I let x be 0, I would have 0 over y squared, which would be 0, and vice versa. So if this limit exists, it must be 0. We could look at other paths, but that doesn't prove that the limit actually exists. So let's assume my numbers x and y are real numbers that are close to, but not equal to 0. We know that 0 is greater than or less than or equal to x squared, since I would square it to make it positive. I can then add y squared to both sides to say that y squared is less than or equal to x squared plus y squared. I can then divide both sides to say that y squared over x squared plus y squared is less than or equal to 1. Multiplying both sides by x squared then gives x squared y squared over x squared plus y squared is less than or equal to x squared. But since I know that this is also approaching 0, since x is approaching 0, I now have that this limit is somewhere between 0 and 0. So that tells me that yes, the limit actually does get to 0, because I know that this is approaching 0 and it has to be a positive number.
If you would like to see Professor Pierce make more videos like this one, you can support her on Patreon in the link below. Any and all support means a lot to her. It allows her not only to make more videos, but it also allows her to campaign for free and accessible online education to conferences and other universities. Thank you for watching, and remember, math is for everyone.